Hello. I'd like to talk about the second derivative test with you, which is a way for classifying critical points when doing optimization. I think it is like that. It's not the second of the derivative tests. It's the test that uses the second derivative. This is in the world of optimization. Given a critical point, C, does F have a local min there? Local max? Neither? Okay. So there's this kind of flow in the world of optimization. That's like, okay, first find your critical points, and then figure out whether you have optima there. And you've got two choices, broadly speaking, for determining whether you have a local optimum, relative optimum, at a critical point. And those come from the two derivative tests. And we're talking about the second derivative test right now. So I think a picture is probably going to be worth many more words. So let's take a function that looks like that. Let's note where its critical points are. I have a critical point right here, right here, right here, and right here. I'd like to number those. Number 1, 2, 3, and 4. At number 1, we have a local min. At 2, we have a local max. At 3, we have a local max. At 4, we have a local min. And I think I need, okay, so this will be good for now. Okay. So what I'd like you to do is to think about the concavity of this function. The concavity of the function. Which side is the cave side? And I like drawing arrows toward the cave sides. So we call that one concave up because the arrow points up. Up, down, up. And there are these places where the concavity changes, say right there and right there. These 2 points right here are what we call inflection points. Okay, so I would like to make an observation with you, which is that F double prime gives the concavity. And it's really the SI, the sign of it. Here the function is concave up, which means that F double prime of x on that interval is positive. F double prime is positive. Here, in this interval right here, a little further, in that interval right there, F double prime is less than 0 on that interval. So there's tight correspondence between the concavity of the function and the second derivative, the SIGN sign of the second derivative. I would like you to notice that for the relative minima that I drew in this picture, the minimums all have, oh, I missed one. This is supposed to be number 5. Okay. At the minima, they're all concave up, where it's smooth like that, right? The maxima is concave down. This maximum doesn't have well-defined concavity at it because it's not even differentiable there. Okay, so here's our observation so far, is that the sign gives the concavity, and that minima appear to be where concave up. That is to say, F double prime is bigger than 0, and maxes occur at concave down, right? Which is where F double prime is less than 0. Okay, so where the function has a minimum, it's going to be concave up, and where a maximum is going to be concave down, except that that's not always true. The implication is the other direction. That is to say that if I know that my concavity at my critical point is up, then I have a min, and if it's concave down, then I have a max. Okay, and f double prime equals 0 doesn't imply anything whatsoever. Okay, so the second derivative test says that in order to classify a critical point, you evaluate the second derivative at that critical point. So the second derivative test. Okay. Given C, a critical point, if f double prime of C is less than 0, then you have a local max at C, concave down. If f double prime of C is bigger than 0, then you have a local min at C, because it's concave up. If f double prime of C is equal to 0 or does not exist, like that one, then it's inconclusive. Right? And we don't know what to do. The answer is to use a different test and figure out a different way. Okay, so that's a pretty coarse introduction to the concept of the second derivative test for optimization. Given a critical point, this isn't a recipe for how to find critical points. That's something else. Then we can classify the critical point as a min or a max, or fail to, depending on the SIGN sign of the second derivative, and that's why it's called the second derivative test for optimization. Thank you very much, and good luck finding those mins and maxes, my friends. Talk to you later. Bye.